All right then, so we're going to be looking today at horizontal asymptotes. Alex, thank you. This is on page 29 of your unit handout. Once we're done today with horizontal asymptotes, we're going to start exploring tomorrow what the second derivative has to do with the shapes and the behaviors of graphs of functions. Don't forget, chapter 5 is all about graphing functions. So today we're looking at determining equations of horizontal asymptotes, and you have been taught in Math 30 a limited approach to it. Okay, and I will review that limited approach. And it's a limited approach to determining where, if any, there are horizontal asymptotes, because it's only good for certain situations. There are many other functions where what you've been taught in Math 30, it doesn't work for. We're going to be evaluating limits as x approaches infinity, or as x approaches negative infinity, and then using all the previous skills to continue sketching functions. To begin with, here is the definition of why we get a horizontal asymptote. If a function, which is y, if f of x or y approaches some value of y as x gets infinitely small in either direction, so when I say extremely large, I mean it's approaching, x is approaching infinity. And when I say extremely small, I'm talking about the true nature of numbers. Extremely small is negative infinity. Talking about number line descriptions. Then a horizontal asymptote exists at whatever that value that y is approaching is. And we can write that this way. We can say that if the limit as x approaches infinity of f of x has some numerical value, then what you're telling me is that as x gets incredibly large, think of x getting bigger and bigger on a graph. You're moving further and further to the right. What's happening is y is approaching that value L. So if the limit as x approaches infinity of a function is 5, that means that x equals 1,000,000, y might be like 5.001. And at x equals 10,000,000, y might be 5.0000001. It's getting, it being y is getting closer and closer to whatever that limit is equal to. And then as x approaches negative infinity, if the function approaches L, there's a horizontal asymptote. It is very rare for a function to have a different horizontal asymptote at positive infinity than at negative infinity. But it is possible. We are not going to encounter them. I'm not going to talk about them unless we encounter them. Later on in section 5.5, one of the jobs we have is to graph any function using all the skills possible. And there is one question in the textbook that happens to have a different horizontal asymptote at positive infinity than negative infinity. And it's really tricky. It's not something I need to get into unless we get to that question and somebody asks about it. Okay? And I guess what I'm saying is, for now, if you want to know that if there's a horizontal asymptote, you can just do one of these or the other. You don't have to do both. If as x approaches positive infinity, the limit is 5, then there will be a horizontal asymptote at y equals 5 on both sides. On both sides, as long as the function exists over there, right? I mean, it is possible to have an asymptote only on one side because the domain of the function is only over there. So, to give you a visual of this, there's a function. I don't remember what I typed in to get this. Clearly, there's a vertical asymptote there, which means that at whatever value of x there is there, there's an x minus that number in the denominator of the function as a factor. But more importantly, there's a horizontal asymptote. And it's asymptotic in this region because as x is getting bigger, y is getting closer to that value of L. It's asymptotic over here as well for the same reason. So there is a horizontal asymptote at y equals L, whatever that y coordinate is. As x gets bigger and bigger and bigger this way, y is going to get smaller and smaller and smaller, isn't it? But it doesn't continue to get smaller without boundaries. It gets smaller by getting closer to whatever that y coordinate of that line is. So we would say the limit as x approaches infinity of f of x is L, because as x approaches infinity, y approaches L. It never reaches it. On the other side, and I've written things backwards here to include the direction, which I hope you can appreciate what I'm saying. As x is approaching negative infinity, as x is getting closer to a negative infinite big number, y is growing this time. It's getting larger when you look at that side of the graph, because it's asymptotic below. And because of that, we would say the limit as x approaches negative infinity of the function is also that limit. Just like the behavior of a vertical asymptote on both sides of it could be going up, they could both be going down, they could be one up, one down, one up. Same thing here. You can have functions where it's asymptotic below on both ends, above on both ends, or one of each. There is something important, and I want to point this out because sometimes people don't notice it, and then they're doing a problem, and they go, I must have done something wrong. When you look at a vertical asymptote, the graph never touches the vertical asymptote. So, for example, if this is x equals a, we would say without a doubt that the domain, well, that part of the domain, because there could be other restrictions elsewhere, that part of the domain is x can't equal a. That's a fact. If you have a vertical asymptote, the graph will never touch that asymptote, ever. But if you take a look at this, you cannot say y is not equal to L. Sure it is. It's equal to L here and here. Functions can cross, and I don't mean just hop over. I mean be in contact with a horizontal asymptote. The basic reason, everybody, is that functions are allowed to go up and down, but functions are not allowed to go back and forth. So I have a couple of functions here. This first one is 3x squared plus 2 over x squared plus 4x plus 5, and this is what it looks like. There happen to be two vertical asymptotes, some kind of funny business going on in between them. I say funny business because it's not symmetrical in there. It's asymptotic on both sides of this vertical asymptote. It's asymptotic on both sides of this one. It's asymptotic to this will be at y equals 3, this vertical asymptote. It's asymptotic to y equals 3 as x approaches infinity and as x approaches negative infinity. Not only can functions cross a horizontal asymptote, they can do so more than once, and they can do so an infinite number of times. So if I show you this function, and you couldn't analyze it yet because you don't know derivatives of trig functions yet. Looks like this. And as x approaches infinity, y is approaching 5. Every time it flips over and under that y equals 5 line, it doesn't go as far above or as far below, so it's always getting closer. Which is a pretty cool kind of thing. It's got some trigonometric nature to it, and it's also got some rational nature to it in terms of asymptotes. Okay, so how do we find these limits? We have to use this basic idea. We find limits as x approaches infinity by knowing that I'm going to start with the limit on the right. And I just want to rewrite it so that I can see it a bit larger. We need to know that this limit is equal to 0. R is a positive number. Okay? It doesn't have to be a whole number. It doesn't have to be an integer. It's a positive number. It has to be, it doesn't even have to be rational. I don't know why I've got the word rational there. Maybe I should use real. Okay. And this is the reason, and I can take examples to illustrate this. The limit as x approaches infinity of 1 over x to the 1, well, we talked about this yesterday, actually, in a different context. Well, even just today, we talked about this today in a slightly different way. In the example that Fazile asked about, the bottom was getting infinitely small, right? So the whole thing got infinitely big. Here, the bottom is getting infinitely big, which means the whole thing gets infinitely small. Basically, everybody, 1 divided by infinity is 0. 1 divided by infinity squared is 0. 1 divided by infinity to the 1.3 is 0. 1 divided by infinity to the 113 is 0. 1 divided by x raised to a positive number will always give you 0 when you use x approaching infinity. The fact that in calculus we like to say, and that's true if x is a negative number, it doesn't play any role. The fact that it's negative doesn't play any role in this statement. I'll use 7. If x is 7, okay, and you're putting in a large number, or x is raised to the 7, and you're putting in a large number for x, you're putting in maybe negative 1,000,000. The fact of the matter is, the bottom's going to be negative, isn't it? Because you're raising it to an odd exponent. But the bigger picture is really, really big. That's what's important. So the whole thing is 0. This, with an incredibly large value of x in where the negative is going to be 0 for the same reason that raised to the 8 will be 0. Whether it's divided by a positive, infinitely big number or a negative, infinitely big, doesn't matter. So this is the key. And as I said a few minutes ago, since the asymptotes we're going to be dealing with initially are the same at positive and negative infinity, we can just worry about that. So algebraically determine any symmetry, intercepts, extrema, asymptotes, and sketch the function. Well, let's start off with the x-intercepts. Yes, it's true that this is where y equals 0, but with a rational function. I just want to rewrite this. And I feel as though I don't want to repeat myself over and over again, so I will say, anytime I talk about a rational function, I'm talking about positive exponents. I'm talking about somebody has simplified it into a nice form. The x-intercepts are found by investigating the zeros of the numerator. Because we don't need to do this. You could say, I'm going to make y equals 0 and solve that equation. But the only way that fraction will be equal to 0 is if the numerator is equal to 0. So we will have x-intercepts at plus or minus the square root of 1/3. And I hope everybody's with me on that. You set 3x squared minus 1 equal to 0. Add 1 to both sides, divide both sides by 3, take the square root. What about the y-intercept? Well, the y-intercept is where x equals 0. But that's just a matter of putting 0 in for x. And I feel, though, at this level, I shouldn't have to write out 3 times 0 squared minus 1 over 0 squared minus 1. You're going to get negative 1 on the top over negative 1 on the bottom. You're going to get a y-intercept at 1. What about vertical asymptotes? Well, that's going to require us to rewrite this function in factored form. Now, we've talked about this before. Is it possible for you to factor the numerator as a difference of squares? Yes. Root 3x plus 1, root 3x minus 1. There's nothing to be gained by doing that. There's no profit in that move. However, and you could argue we don't actually need to factor x squared minus 1 either, but I'm going to anyway. I hope you see that you have non-permissible values of 1 and negative 1. And that the two factors that produce those non-permissible values do not cancel with identical factors on the top. And what that means is you have vertical asymptotes at x equals 1 and x equals negative 1. Now let's talk about the horizontal asymptote, which is new. So I'm going to pull up the Math 30-1 rule that you learn for horizontal asymptotes. It's locked up, so I'll just have to explain it verbally. I'll see if I can find a graphic for you a little bit later. How many of you remember the rule? Shaky hand, remember? What do you remember? Okay, so let's start with that. Oh, and that's this, isn't it? The rule is that if the polynomial on the top, now this rule is going to break down when it's not a polynomial. What if it's radicals? It won't work. But the rule is if you have a polynomial on the top and a polynomial on the bottom, if the highest degree on the top is the same as the highest degree on the bottom, then you will have a horizontal asymptote at the ratio of the coefficients of those highest degree terms. Do you remember that now? So you will have at y equals 3 a horizontal asymptote. Eli, do you remember what happens if the degree on the top is smaller than the degree on the bottom? It's at 0, y equals 0, the x-axis. Do you remember what happens if the degree on the top is less than or is more than the degree on the bottom? There is no asymptote. So you had these rules. And it will work in this case, but it's limited. So here's what we're going to do instead. For our horizontal asymptote, we are going to find the limit as x approaches infinity of the function 3x squared minus 1 over x squared minus 1. Now, it's not easy. You have to be shown how you can actually determine this now. In Math 30-1, I never used limit notation, but I would have told you that as x gets really, really big, if y settles down to something, then wherever it settles down is the location of the horizontal asymptote. And what we did in 30-1 is we would have started putting in really big numbers for x. That's not what we're going to do. What we are going to do is rewrite this and divide every term on the top and every term on the bottom by the highest degree on x. So I'm dividing the top by x squared, and I'm dividing the bottom by x squared. And we can simplify that now. On the top, we have the limit as x approaches infinity. On the top, we have 3 minus 1 over x squared. Because 3x squared over x squared is just 3. And on the bottom, we have 1 minus 1 over x squared. And now we can substitute in what x is approaching. Because when I substitute x equals infinity in, and I know that that's an absurd idea, but I'm telling you I'm putting in an infinitely large number for x. 3 is not swayed by what x is. 3 is 3. But 1 over x squared will be 0, because the limit as x approaches infinity of 1 over x to a positive exponent will be 0. And then 1 minus 0. So this is equal to 3. What have we learned? We've learned that there is a vertical asymptote, a horizontal asymptote at y equals 3. And as I said, you could probably just look at that function and go, yeah, y equals 3. And that's fine. But later on, you can't always do that. What have we got? We've got all our asymptotes. We have all our intercepts. Let's talk about symmetry. And I'm working with kind of not really infinite, but an incredibly large work surface. I'm scrolling up and down all over the place. You've got a limited piece of paper, but you've got enough room. What about the symmetry? Well, the function is f of x is equal to 3x squared minus 1 over x squared minus 1. I would like everybody to determine whether that is odd, even, or neither. I don't think there's really any work that we need to show here. It's even. Because if you put negative x in for x, you'll get the same function. So this is even. So now we have the intercepts, x and y intercepts. We have all of the asymptotes. We know that it's even. And now we need to determine max mins, which means we need to differentiate that function. I have no doubt that everybody can differentiate that function. So for that reason, I've already got it up here. Let's not spend class time doing something that we know how to do again and again and again. Is it good practice to be able to find this derivative? Well, sure. But we also have to be mindful of the amount of time we have in class. Okay? So it turns out that the derivative, I guess I'll have to move this down. It turns out that the derivative is equal to that. So I'll give you a second to write that down. You could do that easily by applying the quotient rule. What this means is that the critical values of the derivative will be 0 and plus or minus 1. Why 0? Because there's a factor in the denominator or the numerator of x. Why plus or minus 1? Because there's a factor of x plus 1 and a factor of x minus 1 in the denominator. Since it's even, we have to have critical values of x that are reflected horizontally from each other. You couldn't have a critical value of x of 1 and negative 1 and 0 and then have another critical value of x of 5 unless you had negative 5. When we set up our first derivative table, we'll put negative 4x, x squared minus 1 squared, dy dx, and then y. I'm sure we've covered this before, but the derivative has negative 4x over that thing. The table doesn't show we're dividing by it, but when you multiply negatives and when you divide negatives and positives, the rules are the same. I'm going to put for my intervals negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to positive infinity. And then we're going to populate that table. Negative 4x will switch signs as we cross the 0 of negative 4x, which means before we get to x equals 0, the sign on negative 4x will be the same everywhere, and after it will be opposite to that everywhere. Since it's negative 4x, it will be positive originally, and then change to negative. This is a breeze. It's positive everywhere. Because the derivative has a denominator that's squared, I don't need to worry about all of the factors changing from positive to negative anywhere. The whole thing is squared, so it's all going to come out as being positive. Which means the derivative is positive, positive, then negative, and negative. And now our job is to piece it all together without the use of a graphing calculator. Okay? So, I'm going to be going by memory here, but I think I have most of this. Would you agree that there was a vertical asymptote at 1 and a vertical asymptote at negative 1? Okay. Before I draw them in, were there any other key features in terms of x? Well, when we look at our first derivative chart, the function is increasing, then it's decreasing and decreasing. And what that means is that we have a maximum here. We have a maximum there, which is at 0 comma something. Because the critical value of x that increasing, decreasing happens through is 0. We put 0 in for x and we get, well, we already knew this, that's the y-intercept, right? So there's no other real important numbers x-wise, which means in my mind, when I go to sketch this or to scale it, I'm thinking that I can put a vertical asymptote here and here. So I'm scaling it so that my graph is going from about negative 2 to positive 2. If you want to scale it so it's going from negative 5 to positive 5, I don't care. I just think that going that far left or right, you're not showing any new information. Now, I mean, I shouldn't have been so judgy there. We do have other x numbers that are important. The x-intercepts, right? But I guess I kind of in the back of my head knew the x-intercept is going to be less than 1. It's the square root of 1/3, isn't it? I want to say 0.577. One over root 3? 0.577. So that would mean that we have an x-intercept approximately here and approximately here. And in the sake of, again, being mindful with the time we have available to us, I'm not going to label those. If you want to write in there 1 over root 3 and negative 1 over root 3, that's fine. Is something funny? Did I do something? No? What happened? Oh, there was some... Hijinks in the hallway? Okay. So you can label those if you want. We also have a y-intercept of 1. Now, I think it's pretty clear here what this middle part of the graph is going to look like. Right? I'm going to actually move this down a bit to make it easier to draw. It's going to be, it's not a parabola, but it's going to have that overall shape, and it's going to be asymptotic to those two lines. Okay, and we'll get to that in a second. We also have, though, and I do need to move this down. Why? Because I want to leave room for the y equals 3 asymptote. That was another piece of information we knew. So if that's 1 for y, this is 2. The horizontal asymptote is about there. I just want to do a quick estimation here. Close enough. As I like to say, we're not, inventing a vaccine here. It doesn't have to be perfect. He says as he perfects it. Now, what will the graph look like? There's something that we didn't do, and I'm always hesitant in doing it because you probably don't need to. It's this, that really you should be also finding this limit. Why? So we can find out whether the function is approaching positive infinity or negative infinity on the left side of the asymptote x equals 1. And then we have to do the same with approaching from the right, and then we should do the same with the left and the right of the other asymptote. But here's why you almost always don't need to go that far in your investigation. When you take a look at your first derivative, and here's where I do need your help, up to, we had a critical point here, we had a critical point here, we had a critical point there, correct? Up to that first critical point, the first derivative was positive. And then it continued to be positive, and then it became negative and continued to be negative. Are you with me on that? And I wrote y prime despite it making my skin crawl because I just didn't want to squeeze dy dx in there. But what that means is y, the function, is increasing in these two intervals and decreasing in these two. There's only one way you can graph this so that it follows that behavior. If it's asymptotic to this asymptote and this asymptote, and the function is increasing from negative infinity up to that first asymptote, the graph must look like this. It has to. There's no other way you could draw it. Similarly, it has to look, because of the asymptotic nature in this corner in the top right, it has to look like that. If it's increasing immediately after the first asymptote, and this point at 0, 1 is a max, well, there's only one way you can draw it so that it's asymptotic to those two vertical asymptotes. And it's like that. And don't worry about your artistic ability. It'll get better and better. It doesn't have to be perfect anyway. I'll just change the colors here so that it's very clear what we're talking about, that that's the function. And I'm not going to spend class time here graphing it on the graphing calculator. It will be fine. It will match perfectly. Any questions with that one? Okay, let's pick up the pace now for the second one. We have this function. It's neither odd nor even, because if you put in negative x here's what you would get. If you put in negative x, you would get negative 1 over negative of x cubed minus 1. And that is neither the same as the original function, nor is it negative. Okay? So it has no symmetry. Intercepts. The graph goes through the origin. When you look at the numerator to determine your x-intercepts, there's a factor of x, which means a 0 of the function is the number that makes that factor 0, which is 0. But if you have an x-intercept of 0, the y-intercept is 0. You can't have an x-intercept of 0, but not a y-intercept of 0, or vice versa. So we know the intercepts. There is a vertical asymptote at x equals 1. And when I do the vertical asymptote, I am looking at the denominator, right? I'm going to now find the limit as x approaches infinity of x over x cubed minus 1. Listen, if you want to take the shortcut here, you can. It will be 0, because the degree in the numerator is smaller than the degree in the denominator. But I'm going to divide everything in the numerator and denominator by x cubed. That's your rule. You divide everything by the highest degree, x to the highest degree. So I end up with 1 over x squared on the top, 1 minus 1 over x cubed on the bottom, which is equal to 0. Because this is going to now be 0 on the top over 1 minus 0 on the bottom. Because these things I'm highlighting become 0 at infinity. So we have a horizontal asymptote at y equals 0. And in the previous example, we probably spent 20 minutes doing all of that. I think these preliminary things are something that should take you 5 minutes. Now, we also have to determine max-min, and again, because I've taught this lesson a lot over the years, I know that if I expected us to find the derivative here, I would be overly ambitious in thinking we could actually get it done in one class. It's too much work. So I'm giving you the derivative. That is the derivative of the function. What this means is we have critical values of x of the cube root of 1/3 or 1. Nope. We have critical values of x of 1 for the denominator and the cube root of -1/2, which is negative of the cube root of 1/2. There's lots of ways you could write that. You know, if you want to, you could write it that way. Because the cube root of 1 is 1, so it's negative of 1 over the cube root of 2. And when it's 1 over, it's raised to a negative exponent. Just because we're going to need to know this number later, can somebody find out what this is equal to about? So take 1 divided by 2, take the cube root, and then switch it to a negative.
Negative 0.79.
Anybody else? So we'll just keep in mind that this critical number is, there's 1 and about negative,
0.79.
I'm just going to say 0.8. Okay, that's so that we know where to put it if it becomes important on our graph. What will our derivative chart be? Well, it will go from negative infinity to the cube root of 1/2. That's the same number. I'm just writing it as 1/2 raised to the third. It will go from 1/2 raised to the third to 1, and from 1 to infinity. Across the top, we are going to have negative 2x cubed minus 1. We are going to have x cubed minus 1 squared and I wouldn't, honestly, I would not take any chances with that negative 2x cubed minus 1. I wouldn't go, oh, it's going positive to negative, or I think it is going to go positive to negative. I'm pretty sure it will be this. But what you might want to do, because I'll tell you what, if you try to graph a function and you've got one piece of the puzzle that's wrong, you'll go nuts trying to make it work because it just won't work. So you might want to, cheat a little bit here and go negative 2x cubed minus 1. That's that factor. Go to your table. Put in a number that's in this interval, like negative 5. I get a positive. Put in a number that's in the next interval, 0.9. I get a negative. Put in a number that's in the third interval, 8. I get a negative. Okay, so you just want to make sure, by hook or by crook, I don't care how you populate that table, you do it. And x cubed minus 1 quantity squared is positive everywhere. So the derivative is positive, then negative, which means y is increasing, then decreasing, then increasing. Which means we can add something to our list. Decreasing. The thing we can add to the list is that we have a maximum at 1 comma something. Right? The function goes from increasing to decreasing, at this comma something. It goes from increasing to decreasing as we pass through that critical value of x of 1/2 raised to the third. So now we want to find a y coordinate because we're going to have to plot it. Which means you have to take that number, and I'm not worried about exact values. And you're taking that number and you're throwing it back in here. So you're taking the cube root of 0.5, the negative of the cube root of 0.5, and you're putting it in there. And I want a few people to tell me what we get so that we've kind of got a consensus. Have you got it, Jay? Yep, but you're hesitant to say? Okay, so 0.5,
529.
529, so 0.53. And this is actually negative, isn't it? Yeah. But you do get a positive, is that what you're saying? Okay. Okay. So now we have to put this all together. And you might want to keep something in mind. We have one more layer on top of this that we're going to be adding tomorrow. So it's growing. It's going to be do all this plus that other thing and then sketch it. All right. We have an intercept at the origin. We have a horizontal asymptote that's the x-axis. We have a vertical asymptote at 1. We have a maximum at approximately negative 0.8, comma 0.53. So negative 0.8 was over here, approximately. 0.5, well, I don't think it really matters here. 0.5, we'll just say 0.5 is here. So this is the maximum. I'm going to put across the top what dy dx is. And I'm pretty sure, but you have the data tables and all of the information in front of you, that we had a critical value of x at negative root 1/2, a critical value of x of 0, and a critical value of x of 1. By the way, any place you have a vertical asymptote, that will be a critical value for x. It will never correspond to a maximum. And I believe I got to look at this now. So we did not have a critical value of x at 0, right? It was just at the cube root of negative 1/2 and at 1. And the function had a negative derivative and then negative again. The fact that the function goes up, then down, past the cube root of negative 1/2 tells you that that's a maximum. So what is the only way you can draw this? Well, in the top right corner, the only way you're going to be able to draw this is that way. I don't care how precise the curve is. Resist the temptation, though, to do this, because I saw a couple of you do this yesterday. Don't draw it this way. You know, have some curviness to it, not almost straight down and then almost straight to the right. How is it I can draw a function that is asymptotic here, asymptotic here, so that it goes through the origin and it goes through that other point, which is a maximum? Here's a subtlety. It has to be curving this way. It has to have that kind of bend to it to be asymptotic. But, everybody, if this is a maximum, it has to have the opposite kind of curve as it goes through that point. It has to be curving, if you look at my hand, kind of in this way against the asymptote, but as it passes through the max this way, which means there's an inflection point. So the graph is going to go like this, through here, down, and be asymptotic. And again, you can check that against your graphing calculator. That's fine. It will be good. Resist the urge when you're working on any of these, and we're going to be getting lots of practice with graphing over the next week. We're pretty much into the rest of the unit now, how to graph. Resist the urge to look at your graphing calculator. If you are getting incredibly frustrated, then check your derivative against Wolfram Alpha or some other program. Have I talked about Wolfram Alpha with you? Wolfram Alpha is a mathematical search engine. So if you type in water in Wolfram Alpha, it will tell you everything there is mathematically and scientifically about water. If you type in this function, it will tell you everything about the function. It will tell you the first derivative. It will tell you the second derivative. It will tell you if it's factorable, if it's simplifiable. It will tell you the zeros. It will show you a graph. So Wolfram Alpha, you can get an app for it just on your phone. You can type in the function, and it will tell you what the derivative and second derivative are, so you can check to see if you've done it right. Because believe me, if your derivative's wrong, like imagine trying to graph that if one piece of your derivative chart was backwards. It wouldn't make sense. Okay. So what is new today? We're not going to do example 3 today. We'll probably do it tomorrow. What is new today is finding those horizontal asymptotes. Okay. So if we take a look at the questions that I've got attached to this, and we might not even do example 3 because it's kind of not important, but we'll see. Make sure that you know how to find limits as x approaches infinity for any of the questions in number 2. And make sure that you can do 3 and 4. Okay? Do not worry about 5. And I might show you 5 tomorrow. It's example 3, and I don't even know why I include it. But so I hope you also know that if you're finding these limits, what you are doing is finding an asymptote. And I have no objection with you looking at this and saying this limit will be equal to 1. Because the degree on the top and the bottom are the same.